to calculate the infinite sum from 1 all the way up to infinity of arctangent of 1 over 2k squared. And first we're going to prove this lemma. Arctangent to x minus 1 over 1 plus xy is equal to arctangent to x minus arctangent to y. Because the first reaction when you saw this arctangent, so immediately we want to use the difference between arctangents, or the difference between tangents, so that we can maybe perhaps at some point use the telescoping, turn it into a telescoping function series. So first of all, let me just say tangent of alpha minus beta. And we have the formula. Tangent alpha minus tangent beta over 1 plus tangent alpha times tangent beta. Right? If we just let tangent alpha equal to x and tangent beta equal to y, right? Then we immediately can say that arctangent x is equal to alpha, and arctangent y is equal to beta, right? Alpha beta just denotes the angle in arc. So in other words, we can just take the arctangent of both sides, right? Arctangent of tangent alpha minus beta is just the angle itself, right? Just alpha minus beta. And alpha minus beta is just arctangent x minus arctangent y, right? And that is equal to arctangent of the right-hand side, right? So arctangent of tangent alpha minus tangent beta is just x minus y, x minus y. And 1 plus tangent alpha tangent beta is just 1 plus x times y, right? So we've derived this identity. So now my job is to somehow turn 1 over 2k squared into something that's simpler, so maybe perhaps more complex. And so how can it determine what is x, what is y, right? I want to, because we don't have 1 plus something here on the bottom. Somehow I want to make 1 appear, right? So how about this? How about 1 over 2k squared? How about I let it equal to just 1 over 1 plus 2k squared. I have the minus 1, right, to make it the same. So can I write it in this way, right? And then determine, because I want to make sure that here I have the x times y. So can I turn this into x times y and determine which is x and which is y, right? So can I perhaps write it into 1 over 1 plus, this is a difference of perfect square, right? So square root of 2 times k plus 1 times square root of k minus 1, right? Is it doable? In other words, can I treat square root of 2 times k plus 1 as x and square root of 2 times k minus 1 as y? Is it doable? Right? So in other words, if I want to say that x minus 1 appears on the top, right? So in other words, is 1 equal to x minus 1? X minus y, right, square root of k, plus 1, minus square root of k, minus 1. Is it equal? No. Right, appears to be 1. So in other words, this is not actually doable, no. Somehow I can make some little change to it and somehow make it work, right? Since I have 2 instead of 1, so that motivates me to multiply 2 on both top and bottom to this one, right? So in other words, 1 over 2k squared can be written as 2 over 4k squared, right? Again, I want to make 1 plus xy appear on the bottom, so what do? I just rewrite it into 2 over 1 plus 4k squared minus 1, right? And further, that is equal to 2 over 1 plus, again, difference of perfect square, 2k plus 1 times 2k minus 1, right? Still the same thing. Now this time I can let x equal to 2k plus 1 and y equal to 2k minus 1. Can I double check that if x minus y, is it equal to is it equal to 2, right? X minus y. 2k cancel out. 1 minus 1 plus 1. Yes. So I've just worked out the 1 over 2k squared is equal to this format, and I treat 2k plus 1 as x and 2k minus 1 as y. Turns out their difference is really 2, right? Equal to the top. So let me just write down top is equal to 2k plus 1 minus 2k minus 1. Bottom I have 1 plus their product, 2k plus 1 times 2k minus 1. Now I can just legitimately apply my lemma, right? So arctangent just this, right? 1 over 2k squared is legitimately equal to arctangent right? So arctangent to this, which means arctangent of this, right? xy is equal to arctangent of this minus arctangent of that, right? Arctangent of 2k plus 1 minus arctangent of 2k minus 1, right? So all I need to do is to look at the finite sum, right? K from 1 up to n of arctangent 1 over 2k squared, right? That is equal to arctangent to k from 1 to n of arctangent of 2k plus 1 minus arctangent of 2k minus 1, right? In other words, k from 1, right? So first I have arctangent of what? 3 minus arctangent of 1. Right, then I have arctangent of 5 minus arctangent of k equals to 2, right? 3, right? So on and so forth. And until arctangent of 2n plus 1 minus arctangent of 2n minus 1. So what's the pattern here? So arctangent of 3 and arctangent of 3, they just cancel out. So the pattern is simply, it's always the former of the first pair cancels with the latter of the second pair. Right? So according to this pattern, I still have this term, but somehow, like I said, the former of the first pair cancel with the latter of the second pair. So this should cancel with some other term, right? The latter of the next pair. And this pair, right, remember, its former pair, the former of its previous pair cancels with the latter of this pair, right? So this pair cancel with some other pair, right, previously. And I'm left with this and that. Right? So if I let n approach infinity, right, it says to infinity. So n approach infinity. So this will turn into arctangent of positive infinity. What is that? Half pi, right? So I have half pi, and I still have this, minus arctangent of 1. And arctangent of 1 is what? Just a quarter pi. The reason is because tangent pi over 4 is equal to 1. So that's actually equal to pi over 4.